Hello for another video snippet on stress and strain in the chapter on elasticity. So we introduced elasticity for a wire by extending the wire. You may remember that. Suppose I have a steel wire and I put load on it, put some weight on it, and the wire kind of extends. Thickness also changes a little bit, okay? But we're not worried about thickness yet. But just looking at the length change, when we look at inside, we see that every little piece here has become a little bit longer over there. So if you look inside molecular level and atomic level, what you will notice is that you can model them as being bound by some springs. So the springs have become longer in a sense. So manner speaking, those, and so this, if they were really truly springs and they get longer, they will try to pull inward, right? If you lengthen the spring, what happens? What it does to the ends, it tries to pull them in, right? So that's what's going on. So those forces are developed, and so there will be some average net force that acts over this entire area of cross section. So that force divided by area crossing stress. If you trace that down, and if you look at this area, this particular element, you will say, hey, that those forces are basically this for balance. The weight is balanced by that force. So this force inside is nothing but the weight, right? Is equal to the weight. These are not accelerating. So this particular point mass must be balanced, right? Forces must be balanced. So this F and this mg are they equal to each other. So stress inside the material is actually here. Here is just the weight that you have put on, weight of the load that you put on, and the area of cross section. So that's the stress that is developed, and the strain is the fractional change. If you look at the whole distance and how much distance has changed. So what's the fractional change? Delta L over L. That we call it strain, or linear strain. And the Hooke's law is this thing: stress is equal to some Young's modulus depending on the material we have, and the strain. So this is the Hooke's law. So that's what we did. Not every material you can do that, right? So if you did a concrete, say you made a concrete wire, and you try to put load on it, you probably can guess it can't extend much. As a matter of fact, it can't extend at all. If you just a little bit of stress you cause inside, and this wire will break. On the other hand, if you take some other wire like a steel, it has a Young's modulus of 200 gigapascal, meaning you can extend it. The concrete doesn't even have Young's modulus. You will say Young's modulus is for any small change, very large stress. So Young's modulus will be kind of infinite. But that's a theoretical, in a sense. It just breaks. Over here it extends, and you can, by using this experimental value, Young's modulus experimental value, you find it by doing the experiment. You do different epsilons and different sigmas, and from the slope, you can read off the Young's modulus. So if I keep adding weight on this also will break. So this is also breaks, but breaks at pretty high 400-500 megapascal stress. You have to cause that much stress to break it. This is called tensile strength. And this is range because you have different types of steel, processing and carbon iron ratio in the steel makes you make different strength steels. Okay, now if you're a concrete, you can actually compress the concrete. You may not be able to extend it, but it's still linearly you can compress it. So you make a concrete column. For instance, in buildings you see concrete columns. They support the weight of the building, right? But if you look at the column versus the length that after the compression, this is different. So there's also a strain in the column. You'll say, well, this concrete will dig into the earth. I'm not talking about just how much it digs in. Assuming they have the same amount of dug in, we're just looking at the length differences now. So this will be the compression will be delta L, and you can change in length over L. You can do a strain, compressive strain. So the fractional change, and there's a Young's modulus for concrete, and this is for the compression. It doesn't work for the stretching of the concrete, but it does work for the compression. Now you can, if you're in building, if you have some experience and read something about buildings, you can't just load up any amount of material above a concrete column. Larger buildings require much thicker columns, right? And because the column will actually give depending on how much stress. So remember, the stress is force over area, right? So if you want higher and higher weight, so higher and higher mg, you need higher and higher A to actually support it, right? And the stress that it can withstand is about 20 to 40 megapascal. 20 to 40 megapascal in concrete. Concrete also varies because of the mixture of things, and you can change the strength of the concrete. But this is a good value. I looked up some handbook. Okay, you can not only change the length, like stretch it and compress it, but you can have material which will actually you can change the volume. You can compress and change the volume, right? You also know, like there this when you have a diving gear, when you dive very deep, the water pressure goes up, and it compresses and actually changes the volume of the container that you are in. Or say you send some steel steel ball down in the water, very deep sea, it will start to compress and change the volume of that ball also. So that's you already know, if you take a gas, which is easily compressible, much more compressible than the steel, and you can push on it and then it will compress. So pressure is actually force over area. We're going to study pressure a little bit more in a couple of weeks. So pressure is already the stress. So if I apply the stress, which is stress will be the pressure, and I compress it from volume to some other volume, so change in volume. So again, this the fractional change, that will be the strain. But here, a strain is actually so-called bulk strain because I'm changing the volume. And the pressure is the stress that I have caused it, okay, in the material. So this force being applied all around it, and so that has caused the stress. Now, the relationship, the beauty of the whole thing is the Hooke's law is the same. Hooke's law looks the same. So you have stress, you have a strain, and there is a constant which depends on the material. like a bulk material, right? So if you look at the bulk stress and bulk strain, this will be called bulk modulus, kind of similar to Young's modulus over there in the length, where they stretch it, compress it. If you look at the steel, bulk steel, Young's modulus steel about 200 gigapascal, bulk modulus steel about 150 gigapascal. Giga is 10 to the power 9. If you look at bone, of course, different bones in human body or animals have different compressibility, and so they compress, they respond differently. But this is a cortical bone, and for that it's about 20 gigapascal. So it's about 1/8 of the steel. The change in, if this is 1/8, so you need 8 times less force to cause the same amount of change, right? So if epsilon was same, then this bone will respond more. So these are some, you can use this in some application, biological application. Another kind of stress is, which is actually the stress by which things deform and change a lot in common day, all right? So if you have some flexible material, you can press on it, but don't press it straight down, you press on the side, the material will change shape. So I have a demonstration here. Nowadays, we have a lot of bread at home. So I'll show you, here's a bread. So look at the angle. See the bread change the angle? So here is the straight. That's the over here. So what I did was I kept the bottom in place, and then I push on the top on the side, and you can see there's an angle that has changed. That angle, the tilt that with respect to the bottom is called shear strain. So this is shear strain. So I've used the same symbol epsilon for this strain. So this angle that I deformed is a measure of how much I deformed, right? I changed the shape a little bit. And so the area over which I applied the force is the top area. And I was applying some force. I was applying all over this area. So amount of force times this area, not that area, it's actually a particular area over which I was applying the force. The area which is responsible for giving this torque that gave me this angle, right? So that force over the area gives me what is called shear stress. Well, guess what? Hooke's law is again applicable here. If these guys are small, then the stress, this is strain, and so there is a constant that's proportion, and here it's called shear modulus. Shear modulus normally are very small, okay, and compared to these things, it's easier to flow, and so if you will see shear modulus in action, like when things like bones break, etc. So it's shears. So shear is a little bit harder property to study, because you can see over here the forces were pushing in, here the push is pulling out, pushing down on it, but here the force is kind of this way, while the change is down here. So geometrically a little bit more involved. You can see more examples of this kind of thing. There are many worked out examples for you at boot camp. Okay. I will stop the video here. I will work out some problems for stress and strain. I will give you some numerical examples of these things in another video.